Hello, my name is Cristian Anacleto-Garcia, and this is my video presentation on crystallization. So in the textbook for our class, we briefly covered some broad ideas surrounding crystals like basic unit cells and different coordinates that can be used to reference different parts of a crystal, but not much light was shed on the process of how crystals come to be. So crystals are pretty much solids that have a specific and consistent geometric structure at the atomic scale. Crystals can be formed from what are known as supersaturated solutions, which are liquid solutions that contain a high concentration of a dissolved solute. Typically, supersaturated refers to mm, a higher concentration of solute than would normally be attained at a given temperature. These supersaturated solutions are attained by heating up the solvent and then dissolving the solute and allowing the solution to cool down. Once the solution is cooled, the resulting mixture could still be in the liquid state while having more solid dissolved in the solution than would normally be possible at the temperature. And in general, crystallization is a two-step process which can only really begin once the supersaturated solution conditions are achieved. The first step of crystallization is known as crystal nucleation, and the second step is known as crystal growth. As we mentioned, crystal nucleation can only occur once the supersaturated conditions of the solution are achieved. And during this nucleation process, the crystalline material, whether it's pure atoms or molecules, they arrange themselves to form the basic unit cells of what will be the crystals. These nucleation sites can form naturally within the solution, or they can occur artificially in a process known as seeding, whereby one would add small amounts of solid crystal into the liquid solution. The structure of the unit cell for these nuclei are determined by several factors as mentioned in the textbook, but one big factor that isn't discussed much in the textbook is the rate at which the nucleation occurs. In the second step of crystallization, we have crystal growth, and the growth of a crystal can only occur at the nucleation sites. Therefore, this would have to be in sequence after the nucleation sites are formed naturally or seeded artificially. The growth of the crystal depends on the collisions of the dissolved crystal material with the nucleation sites. Again, this crystal material could either be a pure material, in which case we would have atoms or elemental atoms, or it could be at the molecular level where we have the smallest molecules of a material. Now, the rate of growth in each spatial dimension during the crystal growth stage can heavily influence the final structure of the material. In some cases, when the rate of growth is very quick, we observe uh, very fuzzy and messy crystals come about. And then in other cases, when we have slow growth, we can see those nice, beautiful geometric shapes that we've come to see in some crystal materials, like quartz, for example. Now, there are several different kinetic models to describe the growth of different types of crystals. Um, the kinetic model that you use would be dependent on which materials you're working with. And all of this is reference to whatever application you're working with. As an example, I performed a short crystallization experiment here at home where I tried to crystallize sugar. So this is a very simple procedure where I just boiled some drinking water. I tried to stay away from tap water because there's some impurities there. So I boiled distilled drinking water and created a supersaturated solution of sugar by dissolving an abstract amount of sugar in about half a liter of water and then letting the solution boil for about 5 minutes after all of the sugar had dissolved to get rid of any excess water. This left me with a simple syrup or kind of like a almost like a corn syrup almost. And I just used granulated white sugar. And then the solution was prepared with a weight and a string where I was hoping to grow the crystals along the length of the string, but the string did not provide enough uh, active nucleation sites for the crystals to grow. So I ended up seeding the solution with small amounts of sugar crystals on the surface, and that's why we see here the sugar crystals that grew along the surface of the jar that I had prepared my solution in. Looking closer at one area of the jar, we can isolate what looks to be a almost cubic crystal growing. This grew on the side of the container, which is uh, generally observed in some non-smooth glass surfaces where the crystals can actually accumulate and form that basic unit cell. Now, an important characteristic here would be that this nice geometric shape that we observe is probably again due to a slow crystallization rate as mentioned earlier, where the slow rate allows for this uniform distribution of the building materials of the crystal. Alternatively, we have another almost nice and square crystal growing on the surface of the liquid. However, we can see that at the top we have a nice square, but as we branch down towards the bottom and the right side of this crystal on the screen, it becomes a little more misshapen. And this is due to varying rates of crystallization and can also be attributed to the fact that the solution was left to cool. So the cooling of the solution changes the structure of the crystal as it cools down. This leads to uneven crystal growth. This in the center of the jar was the largest crystal I was able to grow. And so I was assuming that this was the first crystal to actually begin to grow. And as we can see here, compared to the other crystals, this is completely amorphous. This is not a fixed, beautiful geometry. We can see towards the ends of the crystal where some squares are attempting to form. This is probably due to plateauing of the crystallization rates, where it starts, the crystallization rate slows down or maybe becomes constant. And then the section of this crystal is more circular because the growth of the crystal is random. And again, this could possibly be attributed to higher rates of crystallization. This is just a closer picture of that largest crystal that I was able to grow. Here we can identify certain rigid edges which seem to have 90-degree angles at the corners along only the edges of this crystal. Once we start looking closer to the inside of this crystal, it becomes more of a jumbled mess, and this was because I grew my crystals in a very uncontrolled environment. By the way, these crystals are small relative to the whole jar, and the experiment that I ran was done for about 24 hours. So the crystallization process takes an appreciable amount of time. As we mentioned earlier, the different kinetic models available to describe the rates of crystallization vary on materials, but one very interesting line of materials that I'm familiar with personally from past projects are called zeolites. Zeolites are pretty much porous crystals that have a very high surface area to volume ratio. And now these crystals have a very promising application in things like absorption and CO2 capture. And so these zeolites are leveraged in environmental cleanup projects and sustainability projects. Now, the crystallization rate kinetic model used to describe the growth of these zeolites is known as the Johnson-Melt-Avrami-Kolmogorov theory model. Um, in short, it's referred to as the Avrami model, and this model describes the growth rate of the porous crystals, known as zeolites. The equation shown here is what's used to model the growth of these crystals, and as we can see, the alpha on the left side is known as the fraction of crystallization. This is pretty much just how much crystal is formed over how much total crystal will possibly be formed from the solution. And then we have a variable k, which is known as the rate constant. These rate constants are similar to the rate constants observed in elementary power laws for basic, like some gas and some liquid chemical reactions. And then we have a variable t, which is the reaction time, and a variable n, known as the Avrami exponent. These kinetic models are multidimensional, and one important concept to keep in mind for this specific model is that it only applies at isothermal conditions. So, and even at these isothermal conditions, the Avrami exponents may change depending on what pressures are observed and what materials are used for the specific structure of the zeolites. We can see that these kinetic models get increasingly complex, but they're very important in the application of chemical engineering. In conclusion, there are many different types of kinetic models available to describe the different types of crystallization processes surrounding different materials. It is up to the engineer to determine which ones are applicable for a given application. And it's important that one understands these kinetic models because they are required to design industrial scale chemical reactors to carry out any crystallization reactions. In practice, the kinetic rate laws are used to determine typically a volume of a reactor, things like a continuously stirred reactor and plug flow reactors, which have varying applications depending on one's goal. And the understanding of the characteristics of certain crystals and their associated kinetic models can lead to the optimization of those crystal materials for, again, varying applications. Here are the references in case anyone is interested in doing a little more research on the information I presented here. One really good resource is this last one here, which describes the crystal growth of the zeolites, or the metal organic frameworks that were mentioned that were used in carbon capture. And I just want to take a time to thank you all for making it to the end of the presentation. I provided my email here. In case anyone has any questions, I would be happy to answer them, maybe meet and shed a little more light on the topic, because in general, at USF, we don't cover much of crystallization. It's our introduction to this material is very superficial, but it's very useful. Again, thank you very much, and I hope you all have a wonderful day.